A spacecraft flew across 200 million miles of empty space, reached out to touch an asteroid, and the asteroid nearly swallowed it whole. Not metaphorically. The surface gave way like water, and NASA's own mission scientists later admitted their expectations were, in their words, completely wrong. Stick around because I'm about to walk you through what actually happened when OSIRIS-REx touched down on Bennu. And hit subscribe now because this channel breaks down real space discoveries without the exaggeration. What telescopes on Earth predicted and what the spacecraft actually found were two completely different worlds. And solving that contradiction took years of lab work, laser scans, and a technique originally borrowed from studying cracks in industrial metal. By the end of this video, you will understand exactly why an asteroid that looked smooth from millions of miles away turned out to be hiding something scientists never expected to find. Let's go back to before OSIRIS-REx ever left Earth, because the story of Bennu actually starts with a contradiction nobody noticed at first. Back in 2007, NASA's Spitzer Space Telescope pointed its instruments at Bennu from a distance and measured something called thermal inertia, essentially a way of tracking how fast a surface heats up under sunlight and then cools back down once that sunlight disappears. The readings came back low, really low, the kind of signature you would expect from a beach here on Earth, sand that warms quickly under the sun and loses that heat again almost as fast once night falls. Based on that data, researchers built a mental picture of Bennu as a relatively smooth world, covered in fine, loose material that would be simple to study and even simpler to collect a sample from. Then, in December of 2018, OSIRIS-REx actually arrived. And that picture fell apart almost immediately. Andrew Ryan, a scientist with the University of Arizona's Lunar and Planetary Laboratory, later admitted the team was expecting a few boulders scattered here and there, alongside at least some smoother regions of fine regolith. Instead, it looked like it was all boulders. Large, jagged, unforgiving terrain with almost none of the smooth ground they had been counting on. And boulders that size should behave thermally like solid concrete, holding onto heat long after sunset, not mimicking a sandy beach. The two pictures simply did not match. Fast forward to October 20th, 2020, nearly 2 years after arrival, when OSIRIS-REx finally attempted the maneuver the entire mission had been built around. A brief touch-and-go sample collection at a site nicknamed Nightingale. The plan was simple on paper. Reach down, make contact for only a few seconds, fire a burst of nitrogen gas to kick up loose material, grab a sample, and immediately back away. Every simulation the team had run on Earth predicted a small divot, roughly the width of the sampling head itself, about 12 inches across. A little dust, maybe a few pebbles jumping up, and that would be it. What actually happened looked nothing like that. As the spacecraft made contact, it kept going, and going. Dante Loretta, the mission's principal investigator, described watching the images come back afterward and being stunned. A giant wall of debris was radiating outward from the touchdown site, far more material than anyone expected from something as gentle as a tap. There was no resistance whatsoever. The surface simply gave way beneath the spacecraft like a fluid, and by the time the thrusters fired to pull away, OSIRIS-REx was still actively sinking into the asteroid. It eventually plunged as deep as 30 inches before finally breaking free. For the people actually operating the spacecraft in real time, this was not exciting. It was frightening. A machine worth hundreds of millions of dollars had reached out to gently tap a rock and instead nearly disappeared into it. 6 months later, in April of 2021, the team sent the spacecraft back to photograph the same site again, specifically to see, in Loretta's own words, how big of a mess they had made. What they found was a crater roughly 26 feet wide, more than 3 times larger than the entire 20-foot crater the site had originally sat inside of. To understand exactly what had just happened, researchers led by Ron Balluz at the Johns Hopkins Applied Physics Laboratory ran hundreds of computer simulations, adjusting the surface's cohesion and density over and over again, until the models finally matched what the spacecraft's cameras and accelerometers had actually recorded during touchdown. What they landed on was almost hard to believe. The resistance OSIRIS-REx experienced pressing into Bennu's surface was roughly comparable to pushing down the plunger on a French press coffee maker. Barely anything at all. When the team calculated the density of that surface material, it came out to somewhere between 500 and 700 kilograms per cubic meter. For comparison, an ordinary rock here on Earth typically sits around 6 times denser than that. Kevin Walsh, a geologist with the Southwest Research Institute, who led a second study on the event, explained that scientists had originally assumed fine dust and small grains would settle into the gaps between larger boulders, acting almost like glue, giving the surface enough strength to push back against anything landing on it. That glue simply was not there. Instead, Bennu's surface turned out to be loosely packed and barely held together at all, closer to stepping into a pit of plastic play balls than touching solid ground. The particles were jostling against each other with almost nothing binding them in place. It explained perfectly why the spacecraft sank in so easily, but it still did not fully explain that original thermal contradiction from 2007. Step back for a moment and consider what Bennu actually is at its core. Not a solid chunk of rock at all, but what scientists call a rubble pile. A loose collection of rock, gravel, and dust left over from the early solar system, held together by almost nothing more than its own weak gravity and possibly some electrostatic attraction between particles. It is barely an object in the way we usually think about objects. It is closer to a floating pile that happens to hold its rough shape. And researchers now believe Bennu is not some rare exception either. Many other asteroids scattered across the solar system likely share this same loosely bound structure. Patrick Michel, an OSIRIS-REx team member based at the Côte d'Azur Observatory in France, put it plainly, saying scientists are still at the beginning of understanding these bodies because they behave in genuinely counterintuitive ways. The loose packing explained why the spacecraft sank in so easily during touchdown, but it still could not fully account for the original thermal readings taken back in 2007. Something else, something hidden inside the boulders themselves, had to be responsible for the rest of that missing heat signature. In September of 2023, OSIRIS-REx finally delivered its cargo back to Earth. Nearly 250 grams of dust and rock, 4 times more than researchers actually needed to run their analysis. And for the first time, scientists could examine real pieces of Bennu directly in a laboratory, instead of relying entirely on readings taken from millions of miles away. Andrew Ryan's team had already confirmed that the boulders were more porous than expected, riddled with tiny gaps and pockets of empty space. But when they ran the numbers, that porosity alone only accounted for some of the missing heat signature. Not all of it. Something else was still going on. To dig deeper, a team at Nagoya University in Japan turned to a technique called lock-in thermography, a laser-based method that hits one tiny spot on a rock sample and then tracks how that heat spreads outward through the material, almost like watching ripples move across a still pond. What they found was strange. The thermal inertia measured in these tiny lab samples came back much higher than what the spacecraft had ever recorded out at the asteroid itself, echoing similar results already reported by Japan's own Hayabusa 2 mission. To To scale those small particle measurements up to full boulder size, researchers at NASA's Johnson Space Center sealed samples inside airtight containers under a protective nitrogen atmosphere, essentially giving each rock its own miniature spacesuit, according to curator Nicole Lunning. Scientists could then run X-ray computed tomography scans, peering completely through the container to map the rock's internal structure in 3 dimensions without ever exposing it to Earth's atmosphere or damaging it in any way. And that is when Ryan's team finally found what they had been missing all along. The rocks were not just porous, they were cracked, extensively and everywhere. Once researchers had those detailed X-ray scans showing exactly how deeply the cracks ran through each sample, they fed that data into computer simulations designed to model how heat actually moves through fractured rock. And when they scaled those results up to full boulder size, the numbers finally lined up. The simulated thermal inertia matched almost exactly what the spacecraft had measured out at the asteroid itself. Here is why that detail matters so much. A network of cracks running through solid rock disrupts the normal flow of heat, letting boulders lose warmth far faster than a solid, uncracked rock ever could. Fast enough, in fact, to mimic the exact thermal signature of loose sand from millions of miles away. That single detail finally reconciled the contradiction that had puzzled researchers since 2007. Solid boulders that somehow behaved thermally like a smooth, sandy beach. Ron Ballew's summed up why this breakthrough reaches far beyond just Bennu. For the first time, scientists can directly ground their telescope-based interpretations of an asteroid's thermal behavior using real physical samples pulled from that very same asteroid. It was never a measurement error. It was cracks running invisibly through solid stone the entire time. This is not just an academic curiosity, because Bennu is not some harmless, distant rock. At roughly 1,640 feet wide, it ranks among the most hazardous near-Earth asteroids currently known, capable of causing continent-wide destruction if it ever struck the planet. NASA currently places the odds of that happening at around 1 in 2,700, sometime between the years 2,175 and 2,199. Distant, but not zero. And that is exactly where this loose, cracked rubble pile structure becomes a genuine problem. A solid asteroid might respond predictably to a deflection attempt, a firm push in exchange for a firm reaction. But a body this loosely bound could simply absorb an impact instead, swallowing the force rather than shifting course, or even breaking apart entirely upon entering Earth's atmosphere, creating a different kind of hazard altogether. Kevin Walsh put it plainly: if humanity ever attempts to deflect something built like Bennu, engineers need to know in advance that the surface will not simply swallow the impact. And that is precisely why this discovery matters far beyond one single mission. Reading thermal data correctly from Earth now means predicting the internal structure of asteroids we may never actually visit in person. So what does all of this actually add up to? Bennu looked like a smooth, sandy beach from Earth, turned out to be a boulder-covered rubble pile so loose it nearly swallowed a spacecraft. And the final answer, hidden networks of cracks running through solid stone, took years of lab work to finally uncover. If one small, heavily studied asteroid held this many contradictions beneath a misleading surface, it is worth wondering how many other rubble piles scattered across the solar system are hiding the exact same complexity, waiting for a mission that may never come. As Patrick Michel put it, we are still only at the beginning of understanding these bodies. If stories grounded in real published research are what you want more of, subscribe, and I will see you in the next one.